We'll next take a look at solving trigonometric equations. There are a few things to keep in mind. First of all, you should take in the equation as a whole and consider its structure, because it could be just a linear equation, or it could be quadratic, or something that you need to factor at first before you actually apply trigonometric tools to it. Secondly, you have to be mindful of the fact that applying inverses will only give you one unique root, and you might have to look for more. And finally, to look for the types of restrictions that the equation actually comes with. So sometimes you're asked to look for roots in a particular interval, and sometimes there is no such restriction, which means that you are here after all possible solutions. So we will start with simple equations and proceed to take a look at all different types of equations that can involve trigonometric functions. So this one looks pretty innocent. Sine of x is 2/3. So as discussed in the previous part of this module, we can apply a basic inverse law, or the definition of an inverse sine, to rewrite this as x is sine inverse of 2/3. Now 2/3 is not one of the one of the special angles, which means that I will have to plug this into the calculator and actually look for a decimal approximation. The calculator will give us, put in radian mode, 0.73 radians. Now, in order for us to sketch this, for example, on a unit circle, sometimes it might be easier to imagine this in terms of degrees. So this is approximately 41.8 degrees. Okay, this is all that the calculator will give you as the value of the inverse sine, but this is not a unique solution to the equation that we are actually given. So let's pull up our unit circle here to take a look at what we are actually missing out with the calculator only providing one option. So recall that sine x corresponds to the y coordinate of the corresponding angle. And so here I am told that the y coordinate of the point on the unit circle is equal to 2/3. So sketching that approximately on my circle, here's the y coordinate, here's approximately where 2/3 would lie, which of course looks pretty consistent with the fact that the answer was 41.8 degrees. This does look like about the angle of 41 degrees. Now, however, what the calculation there doesn't show us is that there is, of course, another point right here on the opposite side that will also have a y coordinate of 2/3. Okay, and so here we will have to work the coordinates of that point out for ourselves. So one thing to realize, of course, is that let me make this a little bit bigger so we can see how that works out on the circle. One thing to label this with is 0.73 radians. So if I were to connect to this other side of the circle, this angle is the same as this angle. Okay, so this too will be 0.73 radians. But as the answer, my angle that corresponds to this point is, of course, this whole one. Okay, so the one way to calculate it is to note that, of course, the horizontal line will give me pi. And so to get to this angle, I have to subtract 0.73 from pi. Okay, so the second solution here will be pi minus 0.73 radians. If you are writing this out in degrees, you will then have to say it's 180 minus 41 degrees, which will give you then this angle. Now, there is yet another piece of information that we haven't addressed yet, and that's the fact that this equation came with no restrictions on solutions, which means that I'm not restricted to just the first rotation of the circle. I have to provide solutions for any number of rotations. So this is a solution to the above equation, or this angle rather, right? But so is the angle if I go full circle and then stop here. So is the angle if I go 2 full circles and stop here. So both of these solutions have to acquire plus 2 pi k at the end of them, because 2 pi is the period for the sine function, and k can in fact here be any integer. K is any integer, which will then give us these 2 points on any rotation, clockwise or counterclockwise. All right, moving right along, let's take a look at this next equation. So here we're given 2 cosine x plus 1 equals 2, and the restriction that our solutions should be only between 0 and 2 pi, so on the first rotation on the unit circle. First, I noticed that here, the sine function, sine of x here, was already isolated. Here I have 2 cosines, so I have a coefficient in front of it, and I also have a couple of other constants hanging around. So the first thing I have to do is actually isolate cosine in order to then apply inverse trigonometric function. Right? I also noticed that cosine here is to power 1, which really means that it's a linear equation in the cosine. So I can move 1 over to the right in order to get 2 cosine x is equal to 1. And I can then divide everything by 2 to produce an equation that is very similar in the form to our first one. The solution will be very similar to that of the first equation as well. So let's pull up a unit circle here and think about where cosine of x is equal to 1/2 and what applying the inverse function will give us, and what else do we need to look for. So for 1/2, remember that cosine is the x-coordinate, so x-coordinate being 1/2 is about here. So this is 1 point, and of course the other point will be somewhere here. Okay, so now applying the inverse relationship to this expression or to this equation will give me that x is cosine inverse of 1/2, and 1/2 is one of the special triangles. This will give you the angle of pi over 3 or 60 degrees. So I know right away that this point corresponds to the angle of pi over 3. And now I just need to figure out what this other point will correspond to as well. And just like in the question before, I can connect the 2 points and notice that if this angle was pi over 3, then this angle is minus pi over 3. But now notice that I am restricted in my solutions to be between 0 and 2 pi. So I have to express this angle not as a negative, but rather in this region. So the other way to do it is very similar to what we've had here, is going to be a full rotation minus this little bit. So 2 pi minus pi over 3. So this will be my second solution here. I'm going to have pi over 3 and 2 pi minus pi over 3. If I actually do common denominators on this portion here, I'm going to get that this, of course, remains pi over 3, and this becomes 5 pi over 3. Once again, notice that I am asked for the solutions only in the first rotation of the circle, which means that I do not need to add plus 2 pi k to either of these solutions, because I am restricted in the solutions to only be between 0 and 2 pi. Let's try some other equations that involve tangent and secant and see how we would approach those. So as I mentioned in the beginning, first of all, let's look at the structure of the equation. Here I, again, do not have tangent isolated, but I do only have tangent throughout. It's only appearing to the power of 1 here and a power of 1 here, so it's actually a linear equation in tangent. I can open up the brackets and isolate tangent to be by itself. So I'm going to have 3 tan x plus 3 equals 2 tan x. And then, of course, I can move the tangent all to one side and the constant to the other side. 3 tangents minus 2 tangents is going to be 1 tangent. So I have tangent of x equals to negative 3. Okay, so once again, I can apply inverse trigonometric functions here to give me that x is tangent inverse of negative 3. This is good news, and now I just have to make sure that I don't get any other equation or any other solutions. Here, let's think for a second about the actual graph of the tangent function. Okay, so because tangent is not as easily represented on the unit circle as the x and the y coordinate, it's likely easier to think of the graph of the function itself rather than its definition on the unit circle. So the tangent function looks like this, where it gets repeated periodically with period of pi. Okay, so the original equation here states that tangent of x has to be negative 3, which means that I am looking for -3 on the y-axis, and I'm looking at the solutions that occur along this line. So I can notice right away that on my main basic curve, just my one rotation that gets flipped when I look at the inverse of tangent, there is indeed only one solution here, and then every other solution will appear along the same line, but with a changed or with the added or subtracted period. Okay, so I'm not going to get any extra solutions, but I do have to add a period of pi to this solution that I've obtained using the inverse functions. If you plug tangent inverse of -3 into your calculator, you will get a decimal approximation of what that is, and that is minus 1.25 radians. And again, sometimes it's easier to visualize things using degrees, so if you transform this to degrees, this is minus 71.6 degrees, and we can see that in fact, it is negative here and occurs before negative pi by 2, so that seems consistent. And then I have my plus pi k for all integer k. Okay, so this will be my final solution in this case. Let's take a look at this next example here that talks about secant as the main function involved in the equation. Secant of x is equal to 3, and I have a restriction to be in the first rotation of the circle. Now, secant is easier to be... I could have written tangent here in terms of sine and cosine, but then I would be introducing two different trigonometric functions into my equation. Secant is just 1 over cosine, so transforming it back into one trigonometric function, one of sine or cosine, is going to be fairly straightforward. So this is probably a reasonable way to proceed. So I have that 1 over cosine of x is equal to 3. Then solving this for cosine of x will give me that cosine of x is equal to 1/3. And then this question reduces to the one that we've seen just above it, because this form and this form are identical, with the exception, of course, that here I have 1/2 and here I have 1/3. But the solution will be really very analogous. 1/2 did produce one of the nice special angles, 1/3 will not. So the answer will look slightly more complicated, I guess you can think of it this way, but the inverse function will give me cosine inverse of 1/3, which is approximately 1.23 radian. So I don't have a nice angle like the pi by 3 that I had above, but nothing about the procedure has changed. So thinking in the same way as we did above here, for the cosine of x being the x coordinate of the points, it means that whatever angle I get, which in this case is 1.23 radians, I'm going to get the other angle opposite of it as the second solution as well. So my one solution will be 1.23 radians, and my other solution will be 2 pi minus 1.23 radians. Now, once again, here I am restricted to be within the first rotation of the circle, so I do not have to add a period to my answer, and this is, I'm done right here. This is going to be my final answer here. Let's take a look at the next two equations that both actually have something in common. This is the first time that we're seeing the degree 2 appear, which means that our equations are no longer linear, that I can no longer simply expand the brackets out and isolate the necessary function. I'll have to do something slightly different. Both of these equations can be approached in multiple ways, and I'm going to show you one way to approach this and a slightly different way to approach this, but the methods can actually be interchanged. So I encourage you to play around and see if you can find another way to solve the exact same equation. Our answers should, of course, agree, but the approach could be slightly different. So what I'm going to do here with this first equation is I'm going to try the approach that we've seen before, and that is to isolate sine of x. I noticed that it's only present in one term here, so that's a technique that will probably work. So first of all, I can move 1 over, and then I can divide everything by 2, which will give me sine squared of x is equal to 1/2. And then, of course, I can take square roots of both sides, which will give me sine of x is equal to plus or minus square root of 1/2. Now, it's essential here to remember that when you're taking square roots, you will get the plus or minus. Otherwise, you will be losing half of the roots. Now, what happens next is we're probably going to have to consider the positive and the negatives separately. Okay, so first of all, I can take sine inverse of the positive root of 1/2, and you probably recognize this as one of the special angles, one of my favorite angles, which is pi by 4. And the second one is the negative, so sine inverse of negative square root of 1/2. The calculations here will produce negative pi by 4. So let's pull up our trusty little unit circle to make sure that we take care of all the other equation or for the other solutions that are produced by symmetry. So here I have that my angles are pi by 4 and negative pi by 4. So that's exactly halfway through the first and fourth quadrant. This corresponds to the angle of pi by 4. And this is negative pi by 4, but again, notice that I have to be between 0 and 2 pi. So minus pi by 4 is the same as 7 pi by 4, which is 2 pi minus pi by 4. Okay, now I am solving originally the equation of the sine being equal to plus or minus some value. Sine, of course, is the y-coordinate, which means that these points will have corresponding other 2 points on the other side of the circle with the exact same y-coordinates. So here I'm going to have another point here with the same y-coordinate as the point corresponds to pi by 4. And here I'm going to have another point on this side that corresponds to the exact same y-coordinate as the 7 pi by 4. Now, pi by 4 is a nice angle because it is exactly diagonal, which means that all of these are actually right angles, 90-degree angles. So I can count off by pi by 4s. 1 of pi by 4s, 2 pi by 4s, 3 pi by 4s. So this is what I have here. 4 of them, 5 of them, so 5 pi by 4s. And just to make sure, 6, 7, correct? And 8. 8 pi by 4 is 2 pi. Perfect. So these are all of my solutions. And then notice my restriction here is between 0 and 2 pi. So these are going to be, in fact, all of the solutions. I do not need to add sine period to them. So 3 pi by 4, 5 pi by 4, and 7 pi by 4. Let me once again draw your attention to the fact that you should be very careful when taking square roots to ensure that you include plus or minus, or you would have lost half of the solutions had you simply forgotten to take care of the negative square root here. Now, moving on to this guy, we see, as in the example here, that now I have a power of 2, which means that I'm dealing with a quadratic equation, but also, as opposed to this equation, I have cosine appearing in both terms. Now, this is pretty lucky because that also means that I can factor it out. So let me take out one cosine outside. What I'm going to have left, of course, there's this 2. And here I had cosine squared, which means I'm going to have 2 cosine x left. I have a plus, and if I take cosine out of cosine, I'm going to have 1 left. So be careful here. It doesn't just disappear. It still keeps a factor of 1 behind. Now, factoring is powerful because it splits an expression on the left here into 2 parts, and the product is only ever equal to 0 if one of the parts is 0. So this allows me a way to break up the equation into 2 smaller equations. So this means that either cosine of x is 0 or 2 cosine of x plus 1 has to equal to 0. Okay, so solving these separately, what am I going to get? Cosine inverse of 0 is pi over 2. This is cosine inverse of 0. And then, because it's a 0, thinking in terms of your unit circle here, it's pi over 2, so it happens here. It doesn't happen anywhere else on the unit circle except for this point right here. So I have the 0 occurring at every pi. So, of course, I can write my answer as pi by 2 plus 2 pi k, and then 3 pi by 2 plus 2 pi k. Or I can simply say it's pi by 2, and this happens every pi. So I'm going to take a shortcut here and say that this happens every pi, so I can introduce pi k, not 2 pi k. Solving for the second half is very similar to one of the equations we've seen before. I mean, many of them, right? This equation is, in fact, very similar to something like this once we simplify. So I can isolate cosine, and this will give me that cosine of x is minus a half. Then taking the cosine inverse will produce the angle of 2 pi by 3. And the symmetry around the circle will give me the angle of 4 pi by 3. Okay, so this is produced by cosine inverse of minus 1/2, and this is produced by symmetry. And because here I am asked for solutions, I'm not given the restriction, that means that these guys do have to acquire a period to make sure that we capture all of the solutions. And they are going to get 2 pi k added to each one. Our next example involves some more quadratic forms. So let's take a look at how we will tackle these. Here I have sine squared, I have a sine term, and I also have a constant term. So this is a true quadratic form because this actually looks like a quadratic equation, but where our regular variable has been replaced with sine. So if I simply make a substitution that instead of saying sine of x, I'm going to use a variable y, I can rewrite this equation. So if sine of x is y, then sine squared of x is y squared. Then I have minus 3 sine of x, where sine of x is y, so minus 3y plus 2 equals 0. And so my first order of business is to actually solve this quadratic equation and then come back to the fact that y was actually a function of x. How do we solve this one? There's a number of ways, of course. First of all, we can try to factor it and hope that it's something nice. Here, I have to think of two numbers that multiply to 2 and add to -3. And this is fairly easy. I can have y minus 2 times y minus y equals 0. And as before, factoring is extremely efficient because now I have a product of two things that's equal to 0, which means that one of these things has to equal to 0. And so this side gives me that y has to equal to 2 in order for the bracket to be 0. And this side gives me that y has to equal to 1 in order for the bracket to be 0. Now that I've solved the equation for y, I can come back to the fact that y was actually sine of x and replace it with that. So this gives me that sine of x is 2, and this other side gives me that sine of x is 1. Now, sine of x equals to 2 has no solutions because no angle will produce a sine value outside of the range -1 to 1. So this side gives me no solutions. What about this side? Here I have sine of x is equal to 1. I am only asked to solve this equation for the first rotation of the unit circle. So pulling up a quick picture of the unit circle here, sine of x is equal to 1 means the y-coordinate has to equal to 1. The y-coordinate on the entire circle is equal to 1 only once at this point right here, so at pi by 2. You can, of course, get the exact same information by using the inverse function on this expression, okay? I'm not going to have to add a period to this because I'm restricted to x as being between 0 and 2 pi, so this is my only solution to this equation. All right, let's take a look at this next one. 9 minus sine squared x equals 0. There are, again, a number of ways that I can approach this. I can move sine over and then take square roots of both sides like we did on one of the examples on the page before, keeping in mind that I have to get a positive and a negative square root. But I can also notice that this is a difference of squares. So just to showcase a different approach, this is what I'm going to do. I'm going to notice that the left-hand side is the difference of squares, and therefore I can factor it as such. So remember the difference of squares, this is 3 squared, this is sine squared. So if I factor it, I'm going to get 3 minus sine of x, 3 plus sine of x, If you need more practice with quadratic equations or with any types of factoring of special types of forms or formulas, please take a look at one of the previous modules with a lot more practice for these types of tasks. Now, once we've factored it, we apply the same logic as before. In order for a product to be 0, one of the pieces has to be 0. So I must have that 3 is equal to sine x on this side, and minus 3 is equal to sine x on this side. Now, here, no angle x will produce a sine value that's equal to 3 because the sine values are restricted between -1 and 1. So this side produces no solutions. And same on this side. I can never get a sine value that's equal to -3, which is outside of -1 and 1. So this side also produces no solutions. So this equation altogether has no solutions anywhere, not between 0 and 2 pi or for all real values of x. But that's okay. Some problems have no solutions, and such is life. Let's now take a look at this next set of equations and notice first of all, in this first guy, a big difference between this equation and the ones we've seen before. This equation involves two different trigonometric functions, sine and cosine. All of the equations we've seen up until now had only involved one, and this is an ideal scenario. So we would like, if possible, to reduce this equation to only using one trigonometric function. Now, luckily, this has sine to the power of 2, and we can recall that our basic trigonometric identity, which says that sine squared of an angle plus cosine squared of an angle is equal to 1, can be solved for sine squared x, and then whatever we get can be substituted back in order to actually eliminate sine from the equation altogether. So solving this for sine squared will give us that sine squared x is 1 minus cosine squared x, and we can plug this entire equation, or this entire side, instead of sine, back into the left-hand side here. So what we will get then is 1 minus cosine squared x equals to 2 cosine x plus 2. Now this already looks promising. This looks like the one of the equations we've just seen, because cosine is to power 2, there's cosine to power 1 here, and then there's going to be some kinds of constants, so this is just a quadratic form. Putting all the cosines onto one side together, we're going to get that cosine squared x plus 2 cosine x plus 1 is equal to 0. And again, just like in the example before, you can choose to substitute y for cosine to better see the structure of the equation, or with a little more practice, you should be able to just factor it as is. You can also use quadratic formula if you're more comfortable with that. That's perfectly fine. In this case, this actually works out to be a perfect square. So cosine x plus 1 all squared is what the left-hand side equals to, and that's equal to 0. Now, taking square roots of both sides, we're going to get plus or minus square root of 0 here, which is just 0. So the only solution is what makes the left-hand side 0, and namely cosine of x is equal to -1. Thinking about the unit circle and when that occurs, this will give us only one solution, that x is equal to pi. Notice that here I'm only interested in solutions between 0 and 2 pi, so I don't need to add a period to this, so this is going to be my only solution to this equation. Let's take a look at this equation right here. So notice that I have cosine of 2x equals to cosine of x. Now, this 2 is a part of the angle at which the cosine is computed, so it's not something that I can simply factor out. This is a whole quantity that I'm going to have to deal with as is, but luckily there are trigonometric identities that will allow me to reduce the cosine 2x back down to sine of single x or cosine of single x. There's quite a few identities that actually help you reduce cosine 2x to cosine x or sine x. Here I can see that my right-hand side has cosine of x, so I'm going to pick the one identity for cosine of 2x that involves cos x only. And that is that cosine of 2x is equal to 2 cosine squared x minus 1. This is now my left-hand side, and this has to equal to the cosine of x on the right. Okay, and now I do the exact same thing I've done before. I'm going to move the cosine of x over. I'm going to get cosine squared x minus cosine of x minus 1 equals 0. And once again, you see that I have a quadratic equation here in terms of cosine of x. Once again, you can apply quadratic formula, or you can factor out, or try to factor out. You will get two solutions out of this. Maybe let me write down the factored out form. You should get 2 cosine of x plus 1 times cosine of x minus 1 equals to 0. So we're going to get two solutions resulting from each one. Cosine of x is negative a half, and cosine of x is equal to 1. This equation is the one that we've seen on the previous page, and so we know that the solutions are 2 pi by 3 and 4 pi by 3, each with a period added to them. Whereas this one, cosine of x is equal to 1, again, thinking about the unit circle, you'll notice that it produces only one solution, and that is of 0 plus the period, so plus 2 pi k. Let's now take a look at the last two examples. For this one, I have cosine of 3x is equal to 1/2. So I have a fairly simple expression for cosine, except for my angle isn't just x, but rather is 3x. So I'm going to have to deal with the fact that it's a multiple. I can, of course, try to apply something similar to what we've done here and reduce the cosine of 3x down to some expression in terms of just the cosine, but we're going to see how to deal with the multiples of the angles directly without going through the trigonometric identities. Okay, so first of all, as I said, this expression actually looks fairly simple and would be very easy to solve if this angle in the middle was just x. So let me do just that. Let me first of all give it another name. Let's call it theta. Okay, then my expression becomes cosine of theta is equal to 1/2. And this I already know how to solve. I just need to know the restriction on theta that I have to follow. So here I had that x is between 0 and 2 pi, but theta is 3 times that. So theta is going to have to be between 0, because 0 times 3 is still 0, and 2 pi times 3, or 6 pi. So when I'm now looking for solutions to these equations, I have to make sure that I include not just the first rotation, but also not all of them, but rather just the first 3. Okay, so proceeding like we would normally, I'm going to take the inverse cosine of this, and this is one of the special angles, so cosine inverse of 1/2 will give me just pi by 3. Now once again, recalling our little unit circle, I remember that cosine is the x coordinate, so that's 1/2, and this will correspond then to the angle of pi by 3 given to me by the inverse function. But the same x coordinate is also true for this point on the circle, which is 2 pi minus pi by 3 or 5 pi by 3. Okay, let me make this note here. It's 2 pi minus pi by 3. Okay, so I will have two solutions for theta in the first rotation. So theta has to be either pi by 3 or 5 pi by 3. Okay, now this is just for theta between 0 and 2 pi in the first rotation, but I know that I have to go between 0 and 6 pi for theta. So to both of these, I have to apply two other additional rotations. So both of these will also have to be added, or maybe let me just write them fully out. It's also going to have to be pi by 3 plus 2 pi, 5 pi by 3 plus 2 pi, pi by 3 plus 4 pi, and finally 5 pi by 3 plus 4 pi. Any other additions will bring me over the 6 pi restriction for theta, so these are going to be all of them. Now, my original equation is in terms of x, and this so far is the answer in terms of theta. So I have to turn this answer for theta to be the answer in terms of x. So what is the relationship between x and theta? Is that 3x was equal to theta, which means that x is theta divided by 3. Which means that now I can simply take all of the above solutions and divide them by 3. So pi over 3 by 3 is going to be pi over 9. 5 pi over 3 divided by 3 is going to be 5 pi over 9. pi over 3 plus 2 pi, I'm going to divide each part by 3. So pi over 3 by 3 is pi over 9, and 2 pi over 3 is 2 pi over 3. Okay, and so on. So I'm going to have 5 pi over 9 plus 2 pi over 3. And then I'm going to have pi over 9 plus 4 pi over 3. And finally, 5 pi over 9 plus 4 pi over 3. Okay, this will in fact produce all of the solutions to my equation here. I know it's quite a few of them. Let me try to squeeze them in a little bit tighter. There we go. All right, taking a look at this last one, I noticed that I have a mixture of problems. I have sine and cosine, so not just one function, and I have double angles inside. So I can, again, approach this equation in many different ways, one of which will be to reduce cosine and sine of 2x to cosine and sine of a single x, and then solve from there. But here I'm going to take a slightly different approach. I can also note that while the functions are different, the angles are the same, so I can combine them together to form a tangent, and then solve for one trigonometric function that is tangent. So making an assumption that cosine of 2x cannot be 0, because that would not be a solution to this equation anyway. If cosine is 0, then sine is 1, and 1 is most certainly not equal to 1, so cosine should not be 0. I can divide both sides by cosine of 2x. So this will give me sine of 2x divided by cosine of 2x equals to 1. Sine of an angle divided by cosine of the same angle is the tangent of that angle, equals to 1. And here I can apply the same logic. I can treat this angle inside as one whole until I have to really tease out the values of x for it. So the only thing I have to keep in mind, of course, is the restriction. So the moment I started treating this angle as the one I was solving for, I also had to keep in mind what is the multiple angle restricted between. So my x here is between 0 and 2 pi, which means that my 2x has to be between 0 and 4 pi. So my solutions for 2x have to be in this region. All right, now applying the inverse tangent to this expression will give me that 2x is equal to tan inverse of 1, which is just pi by 4. Okay, so that means that now I have to also apply the period of tangent to my final answer to fit enough times between 0 and pi by 4. So my 2x, which is the angle that I'm solving for without really calling it theta like I did this time, is going to be pi by 4, but then also pi by 4 plus pi, because that's the period for the tangent, and that's still not beyond 4 pi, so I can keep adding. Pi by 4 plus 1 more pi, so 2 pi, that's still not at 4 pi, so I can keep adding. Pi by 4 plus 3 pi, okay, that's still good, but my next one is going to be pi by 4 plus 4 pi. Now I have to be less than 4 pi here, which means that this angle, being 4 pi plus something, is most definitely already out. So this guy no longer fits into my my restriction here. Okay, I also am not going to be subtracting pi because it says that x has to start at 0, and subtracting pi from pi by 4 will get me into the negative x's. Now, so far this answer is in terms of 2x, so I'm going to divide everything by 2 to make it in terms of x. So my x's is going to be pi by 8, which is pi by 4 divided by 2. And then I'm going to have an expression for each one of these. I can, of course, also pull them together. So, for example, pi by 4 plus pi is 5 pi by 4. So my next angle is going to be 5 pi by 8. Pi over 4 plus 2 pi is 9 pi over 4. All divided by 2 is going to be 9 pi over 8. And then finally, pi over 4 plus 3 pi is going to be 13 pi over 4. So divided by 2, it's going to be 13 pi over 8. Okay, and this is it for that. Again, I strongly encourage you to actually take a look at how to solve these equations in other ways, just to get a little more proficient with whatever methods you are more comfortable with. Please take a look at the Webwork assignment module 6D, as well as their exercises at the end of this section that refer not only to the module 6D, but also to the material that we've done earlier in this module in trigonometry, and pull some of the themes about trigonometry all together.